we talked about different types of answers we get with linear equations. We've got one solution, we can have infinite many solutions, we can have no solutions. And so when we're looking at those things, we may get questions like this where it says, hey, how do we change this equation so that we end up getting a certain situation or scenario? And in this case, they want to know, how can we make sure that this equation would give us infinitely many solutions? So I want you to think back and remember from yesterday, what did we notice about both sides of the equation that gave us infinitely many solutions? They equaled themselves. They were the same. So we need the left and the right side to be identical. And if we can make that happen, then we will get infinitely many solutions. So let's go ahead and just kind of clean this up a little bit and see if we can't just keep making small changes until they look as close as possible, and then we'll make a decision about what the value of A has to be in order to make both sides be the same. So on the left side, we can combine like terms, 10x minus 2. All right? That's about as simplified as we can get that, so we don't really need to take the left side any further. Right side, we can use distributive property. Get rid of those groupings. And so we're left with ax plus x minus 2. Well, now we already have something in common, something similar. What do we have that's on both sides? Negative 2. We've got a constant. Our constant is already the same. Okay? So here and here, our constants already match. So we don't want to change our constant anymore. We're good there. The only thing we need to do now is make sure that 10x and ax plus x end up being the same thing. So we can actually just kind of get rid of the plus 2 and look at this. So what does a have to be that if I add 1 to it, I get 10? 9. We can use some inspection to determine, well, a has to be 9. If we wanted to keep going algebraically, we could actually just solve for a. We can take this whole equation and solve for a, knowing that they have to be identical. I can subtract x from both sides. And then I get 9x equals ax. That further reinforces our inspection that a has to be 9. If I wanted to even go further and prove it, I can just solve for a outright. We can just solve for a, and we get that a has to be 9 in order for both sides to be the same and end up with infinitely many solutions. So you may have to get creative and understand those different use cases where we get one answer, infinite solutions, no solutions, and what those equations look like at certain parts of the solution, so that we can manipulate an equation to end up with that result. Okay? Remember when we had a system with no solution? Our coefficients were the same, but our constants were different. Okay? So then we'd have to make sure that the value of a, wherever it was in the equation, made that type of a situation where the coefficients were the same, where the constants were different. We're going to see something similar a little bit further on with some more systems. But first I want to talk about inequalities now. Inequalities follow that same process of solving a linear equation. We want to do distributive property, get rid of our grouping symbols. If we have exponents, evaluate those. If we have absolute value or radicals, evaluate those. Combine like terms, isolate our variable, and solve. But inequalities have this extra step at the end that we have to be aware of. So let's get to that part first, and then we'll talk about it. So distributive property, pretty straightforward. No. Combine like terms. If I've got a -4 and a +2, what does that give me? And if I have a -r and a -3r, what does that give me? -4r less than -14. How am I going to move my constant over to the other side? I get rid of that coefficient of -4 on my variable? Divide, okay? Now this is where we have to be careful, and this is where the inequalities differ. Okay, this is where the inequalities differ. If our coefficient is negative, what do I have to do? I have to flip my inequality. I want to make a special note. It does not matter that that 12 is negative. Doesn't matter, okay? It only matters if the coefficient is negative, okay? That's the only part I care about. If the coefficient is negative, if I multiply or divide, then I need to switch my inequality. So R, instead of being less than, is now greater than +3. Make sure that you're switching that inequality. There's a couple different ways that we can represent linear inequalities in their solution set. This is an inequality statement. Another way that you'll commonly see it is interval notation. Interval notation says, okay, what's the range of numbers? What's the lowest possible value in our set, and what's the highest possible value in our set? Okay. Well, if R has to be greater than 3, what's the lowest possible number that can be in my set? The smallest possible number if R has to be greater than 3. I can go lower than 4. All the way up to 3, but not 3, right? So as close as mathematically possible as we can get to 3. 3.000000000, run out of breath, add a 0 at the end, and then another 1, okay? As close as we can mathematically get to a 3, but not including 3. So 3, for all intents and purposes, is our starting point, but to indicate that, no, not 3, we use a parenthesis. And then, what mathematical symbol do we use if we just keep going forever? So from 3 to infinity. So this is our interval notation, saying that R has to be all values from 3, non-inclusive, to infinity. We could also draw a number line. Number lines don't have to be super complex. I just need 1 point on there. Just a 3. That's the only one I need to know. And then I'm going to use a open circle on the 3 because, hey, we can't include 3, correct? And then we'll shade in. I want greater than. So is that going to be to the right of 3 or the left of 3? To the right. So we shade in that way. So inequality statement, interval notation, or graph. 3 common ways that we represent the solution set for an inequality. Okay, let's do it again with our next inequality. We distribute, and we isolate our variables. Let's add 2x, make that a little bit easier. If we can end with a positive coefficient, that's always better because then we don't have to worry about that sign switch at the end. Okay? If we can make sure that our coefficient is positive, it makes our life a whole lot easier. Subtract 16. Negative 24 is less than or equal to 8x. And again, my coefficient's positive. My constant's not, but it doesn't matter. The coefficient's positive, so I don't need to do a sign switch. My inequality is not going to flip. So I'll divide by my coefficient. Negative 3 is less than x. Now be really careful. Our variable's on the right side. Okay? So sometimes it helps if we kind of flip everything around so that it's a little bit more intuitive when we're reading it. Because I care about the variable and what position it's in. So I'm going to switch this around and I'm going to rewrite it as x. Open side is on the x, so x is greater than or equal to negative 3. I just kind of flipped it around so it's a little bit easier to read and understand that x has to be greater than or equal to negative 3. Now our inequality or interval notation is going to be very similar to our first example, except it's a negative 3 instead of a positive 3. We're still going to infinity because x has to be greater. But the big difference there is I'm not going to use a parentheses. I'm going to use a bracket. Because x has to be greater than or equal to 3. So 3 is included. 3 can be a solution. 3 will make, or I'm sorry, negative 3, will make that statement true. So we use a bracket to say it's included or equal to that number. Parentheses, always on the infinity. Infinity is not a number. So infinity always gets the parentheses. And then the difference graphically, instead of a open circle, what do we use instead? Closed circle. So I'll use a closed circle and shade to the right for greater than. If it was less than, I'd shade to the left. Now, it wouldn't be much fun if we didn't have special cases for our inequalities like we do with our equations. All right? So we go to solve. Distributive property. Combine like terms. What's going to happen when I go to do the next step? On both sides, right? And then what happens when I do that? Yeah, my variables went away, right? My coefficients were the same on both sides. When we have the same coefficient on both sides, we're going to have a special situation. Now, it's a little bit different, but also very similar. We're looking for, is that final statement true or not? So when I look at what I have left, when we had equations, I was just trying to see, oh, is this number equal to this number? Does negative 10 equal 10? Or does 3 equal 7? All right? And we're actually answering that question, yes or no. With an inequality, we're going to do the same thing. Is negative 12 less than 3? Yeah. So we're left with a statement that is, again, always true. Well, when we had an equation and we were left with a statement that was always true, what did that mean about our solution set?
Infinite solution.
All real numbers. Because it doesn't matter what value I plug in for x. That left side will always be less than that right side. Every single time. So we have all real numbers. Or we could use the set symbol for all real numbers. Infinite solution. Many solutions. We could use interval notation. Interval notation would be from negative infinity to infinity. We could draw a graph. Those graphs are my favorite because those graphs don't need any numbers. Those graphs are just completely shaded in. Now, if we get a statement that is always false, say that inequality symbol was flipped and the statement said negative 12 is greater than 3. Negative 12 is not greater than 3. So instead of infinitely many solutions, we have no solutions. It would be that opposite. Instead of having negative infinity to infinity, we would use the empty set symbol. Okay? We would use our empty set symbol. We would say we have no solutions. It's an empty set, and it would just be a blank number line with nothing shaded in, nothing on it. Okay? It's an empty. Those are special cases for inequalities. Any questions on inequalities before we move to systems? All right. Systems of equations. Actually, I think I'm going to go backwards. I'm going to talk about this one first. Go to the last slide, and then we'll go back. Oh, you don't actually have to graph it. But it's important to understand what a system of equations means. Okay? The solution to a system of equations is asking, when are these lines the same? Meaning, Where do they meet? What is the intersection? Okay? It will always be, well, most of the time, it will be an ordered pair. But of course, like with linear equations and linear inequalities, we'll have a couple special cases. We'll go over those, but for the most part, we're looking for an ordered pair, a point on our coordinate plane. So when I look at these two lines, where do they touch? 3, 2. The intersection, 3, 2. That is the solution to the system of equations. Okay? If you are given a system and asked to solve it, and they just say, hey, here's these two equations, don't ever graph it. It's too time consuming and it's inaccurate. But if they give you a graph, you need to understand what you're looking for. You're looking for that intersection point. Okay? You might also need to take a graph and be able to identify what the equations are. And so you need to be able to look and see, okay, if I'm looking at the red line, I need a linear equation. And let's say we'll start with y equals mx plus b. That's our formula for a linear equation. What does m represent? Slope. What does b represent? Y-intercept, which is why it's called the slope-intercept form. So let's look at our red line. What is the slope of my red line? Close. You just said the same number twice. What's the slope of that red line? Is that line going up or down? Negative 1. Going down. Down and to the right is negative slope. So if I start at a point, I go down 1 unit, I go right 1 unit, the rise over the run is negative 1, 1. So my slope is negative 1. What is my y-intercept? It intersects the y-axis at 5. So my y-intercept is 5. If we took this equation right here and rewrote it in slope-intercept form, we'd end up with the same equation. So we know that those two match. Let's look at the blue line. Okay, again, y equals mx plus b. What's the slope for my blue line? 2 over 1. So pick a point, go up 2, right 1, the rise over the run, so my slope is 2. What's the y-intercept? Negative 4. If we rewrote this equation in slope-intercept form, we get the same thing. Okay? So being able to read the graph and interpret the information is there. And then as far as systems are concerned, being able to understand what a solution is. A solution is their intersection. Okay? Now let's go and actually solve mathematically. There's 2 methods. You can use whichever one you want. But there will be times where one method is much simpler or more expedient than the other. And again, when you're racing the clock, anytime you can save, it's time to gain for something else. So substitution usually works best when we can quickly and easily isolate a variable. Like in the case where my coefficients are 1. Super easy to get those, either one of those variables isolated. I could get x by itself by subtracting y, and then boom, I've already got an expression where one of my variables is isolated. Then what I can do is say, okay, well, if x has to equal 6 plus y, or 6 minus y, I can take 6 minus y and put it into my other equation. And when I do that, what I'm essentially doing is I'm getting rid of the second variable. So that's going to leave me with only the variable of y. Now I can solve for y. I can get a value for y because I've eliminated the x by substituting one equation into the other. Distributive property. We'll solve, combine like terms, subtract both sides, negative 5y is negative 10, divide by negative 5, y equals 2. So now I have half my answer. Remember, the solution to a system of equations is an ordered pair. Now I have the y value for that ordered pair. I just need to go back and find the x value. That part's easier. What could I do with this y value to solve for x? And it doesn't matter which equation. Pick whichever one looks easier, the one on the left or the one on the right. Left, because there's less stuff there, right? That's going to be a whole lot easier. So x plus, we're going to replace y with 2. If we're plugging it back in, equals 6. What does x have to equal? What's x going to be? 4. So my ordered pair is 4, 2. My ordered pair is 4, 2. Sometimes the SAT will do something a little cheeky, especially if it's on the student supplied response part at the end where you have to write it in bubble. You can't write an ordered pair in that section, but what you can do is they can say, here's a system of equations. If the solution is the ordered pair x comma y, what is the value of x plus y? So for that situation, what would be the value of x plus y?
6.
6. Okay? Or they could say multiply them. Or they could say put them in this equation and solve that to get a number. So they could have you take that ordered pair and then do something else with it in order to get a single numerical answer that you can then fill in. Now, next process is elimination. To be frank, most of the time, unless substitution is glaringly easy, I prefer elimination. I default to it because it shows some more information that we'll see in a little bit why it's useful. But if it's not your favorite, that's fine. We're going to do it. Okay? Our goal with elimination is to get rid of one of the variables by adding the two equations together. So what we need to do is we need to line up the equations one under the other. And we want to pick a variable to eliminate. You eliminate the variables by having the coefficients be opposite numbers. So usually if I've got one that's positive and one that's negative, I kind of choose that because it makes it a whole lot easier to make those opposites when one of them is already positive and one's negative. So in order for these to be opposites, I need one of them to be a 2 and the other one to be a negative 2. What could I multiply that equation by to turn that coefficient into a negative 2? Not negative 1. I have a negative 1. If I multiply negative 1 by 2, I end up with negative 2. So we'll multiply that by 2. And then I'm going to get 3x plus 2y equals 13. And then 8x minus 2y equals negative 2. That multiplication is the most common thing left out on accident when solving by elimination. So make sure that all 3 terms are getting multiplied by whatever your coefficient is. Okay? Make sure all 3 terms are getting that multiplication. So now we can add these. 3x plus 8x, 11x, 2y minus 2y, that cancels. That's our goal. We want to get rid of that variable. Hey, now the y is gone. And then we get 13 minus 2 to get 11. So x has to equal what? 1. And then what can I do with that value of x to solve for y now?
Plug it in.
Plug it back in. Doesn't matter which one. Let's do the one on the right. 4 times 1 minus y is negative 1. Subtract 4. Negative y equals negative 5. So y equals 5. So my ordered pair is 1, 5. Play around with those. Experiment. See which one works best when. Okay? But if you just can't get elimination, like You tried it over and over and over and it's just not sinking in, that's fine. It's not the end of the world. If you can do substitution, it'll work. There will be times where it's a little bit more time consuming. And if that's the case, you may want to skip that question and come back to it later. All right? But if it works, it works.
Hey, can you ask me?
Sure. Now, the last two things we'll talk about on the next slide are our special cases, consistent and inconsistent systems. It's the same idea that we've seen with the linear equations and the linear inequalities. When we have equations that are the same, we end up with infinitely many solutions. When we have equations that have the same coefficients but the constants are different, we end up with no solution. Okay? So let's take a look at these. This type of situation is why I like the elimination method, because it helps with recognizing a pattern. So I say I stack these because I want to do elimination. Okay? I can multiply my first equation by something that'll let me cancel those out. What should I multiply by? 3. So if I wanted opposite coefficients, I need to change the sign. So I would multiply by -3, which would give me -6x plus 3y minus 9. But then I look and I say, hey, wait a minute. I've got 6 and -6. I've got -3 and +3. I've got +9 and, it would help if I had an equals, and a -9. All the same numbers, but all with opposite signs. So if I continue going through the math, I'd be like, well, wait a minute. That's going to cancel out, and that's going to cancel out, and that's going to cancel out. I'm left with a statement that is always true. Whenever I'm left with a statement that's always true, I'm left with infinitely many solutions. Every single time. If I'm left with a statement that's always true, I'm left with infinitely many solutions. I do want to make a note on this, okay? Because previously we've been able to say all real numbers. With systems of equations, all real numbers doesn't work anymore. Okay? It's specifically infinitely many solutions. And the reason is, let's look at these equations. Let's go back and instead of multiplying by -3, let's multiply by +3. What happens is I end up with 6x minus 3y equals 9, and 6x minus 3y equals 9. They're the same. So my first line, hey, here's my first line. And then my second line, hey, here's my second line. Supposed to be right on top of each other. They're the same line. So they are intersecting at every single possible point on that line, which is why we have infinitely many solutions. But it's not all real numbers. It's only the points that are on that line. So if I asked you if this point over here is a solution to that system, it's not, because it's not on that line. So it's not all real numbers. I can't just pick any 2 points in the solution. But I can pick any of the infinite points on that line, and it is a solution. Consistent system. Inconsistent system. Same idea. Let's stack it. And let's multiply by -2. So I end up with -2x minus 6y equals -8. So in our first example, coefficients and constants were the same. In our second example, coefficients are the same, but the constants aren't. So if we go through it mathematically, well, that equals 0, and that equals 0, but that, go back. Really? That's how you're going to be? No, we're almost done. I don't want to break. Please hold. Alright, so we end up with -5. Does 0 equal -5? That's never going to be true. So again, I end up with a never true statement. Never true statement means no solution. So if a solution to a system of equations is where the lines intersect, what type of lines will never intersect? Parallel lines. If I'm looking at the equation of parallel lines, what about that equation tells me that they're parallel? So if you're given two equations and you're asked to find the solution to that system, if they have the same slope, it's going to be no solution. In order for them to have the same slope, they have to have the same coefficients. Because for both of those, I can take the equations and write them in slope-intercept form, which means I'm going to be adding 2x to both sides. I'll have negative 6y equals 2x plus 3. I'll have negative 6y equals 2x minus 8. Then I'll be dividing by negative 6.
Good morning, students and teachers. Happy Wednesday.
Same slope when we put in slope-intercept, but because the constants were different, then that means the y-intercepts are going to be different. On the left side with the consistent system, because the constants are the same, the y-intercepts are the same, making them the same line. So same slope means you're going to either have infinite solutions or no solutions. It all matters about the constant at that point. If the constants are the same, consistent system. If the constants are different, inconsistent system. Okay? So recognizing those patterns way earlier saves you the trouble of having to evaluate it all the way through. And similar as we saw back here, trying to write a system that's consistent, well, we need the same slope and the same y-intercept. So making sure we get a value of A that matches with that.